Well, today I will discuss on the topic in the quantum mechanics which deal with the measurement in the quantum mechanics and how we can measure a physical variable in the quantum mechanics. So for this, first use the eigenvalue equation, where A operator is an operator form of a dynamical variable A and psi n is the eigenstate or eigenfunction corresponding to the eigenvalue lambda n. So from this equation, if you know a physical variable and its operator form, and you know the wave function of the system, so operate the operator on the wave function, and this will reproduce the wave function with some multiplicative constant, and that multiplicative constant lambda n will be the eigenvalue corresponding to that state, that particular eigenstate psi n. So lambda n is an experimental value, and which is called eigenvalue because it is connected in the eigenvalue equation. But if the wave function is the system should have many number of wave functions like psi n, that is n runs from 1 to infinity because it is Hilbert space I am talking about, and there the infinite number of states are possible, so infinite number of eigenvalues are also possible. But if you do a measurement, then you will surely get the a particular eigenvalue in that case, okay, lambda n. So how this has been done? Because if you are going to measure something, if you are going to measure some dynamical variable by experimental method, you are disturbing the system. That is why the system will be set, or will assume that eigenstate which you have set in your experimental environment. That means if for experiment, you first of all set up an environment for the experiment, and this will be acting like the probe. That means it will surely bring the system into a definite eigenstate. All the eigenstates are possible in a system because it is Hilbert space, and there are many number of eigenstates are possible. You don't know what will come out of the experiment. So theoretically all eigenstates will be considered, but in experimental case, by your experimental setup, you have set up particular you have set up your instruments for a particular set, so you will get that particular result, that is lambda n you will get. If you set an experiment for the third excited state or third state, that is psi 3, or for the eigenvalue lambda 3, you will get that. But in theoretically all states are possible, so you should take all states at a time. That is your basis set, which you know, and that is my next topic, how we will predict an experimental result by taking an expectation value of an observable. So in doing so, or for the to discuss this thing, expectation value of the dynamical variable, let us start from the very beginning of the basis set expansion and to determine the basis set coefficient Cn, which I have not discussed in my earlier classes. Now psi is the total wave function of the system, and un are the normalized wave functions of the system, and Cn is the expansion coefficient of the basis set. So the UNs are normalized, so the normalization equation is there. The limit is from a to b, it is a to b maybe minus infinity to plus infinity. It is generally written here. So um star into un into dx is equal to your lambda mn, that sorry, delta mn. Delta is the Kronecker delta function. So if m and n, that is two states, are not equal to each other, the result will be 0. If they are equal, so result will be 1. That is why un functions are called orthogonal or orthonormal wave function, and they are called that they form the orthonormal basis set psi. Now the process is, first multiply the equation number 1 with your um star on the both side, and then take the integration over the both side. So the left hand side will be looks like this, psi and um star dx integration is equal to cn will be constant, sum over cn will be out of the integration, then um star into un dx. Okay, so and this result we know, all we know that un and um should be equal to each other, so sum will vanish. So what will come, we will get cm, and the sum will vanish, that is the integration will be valid for one case, and this should be 1. So cm will be there, and c um square dx is your 1 we have assumed. So in this line we can write 1, but here it is written later. So cm is equal to integration psi x um star dx. Okay, and this can be written as bracket notation as um bra and ket psi. Okay, bra ket psi in terms of bracket notation. So cm, you can remember either of them because they are similar. So in this way, cn, that is the expansion coefficient, in place of m you can replace n, because we have started with n. So cn, what is the value of cn? Cn is equal to bra un ket psi, or in the integration psi x un star x dx integration is your cn. Now the probability of states. Probability is related with that expansion coefficient. Okay, we will see that in this segment. How the probability we can measure, we know the probability interpretation of the wave function. This is according to the Max Born interpretation, is the probability of finding the particle in whole space from minus infinity to plus infinity if psi is the wave function of the system. Then we wish to find the probability of occurrence of the wave functions unx. See, the probability Pn of the occurrence of the state unx, that is, what is the probability of finding the system in the state unx, because I have told you that the system can be any of the eigenstate, that is u1, u2 dot 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 u infinity. So we are willing here to find the probability of finding the system in the state un. Okay, so in doing so we are going to use the probability formula, that is how we probability measure. It is measured by your statistical formula, where the probability of that thing multiplied by the frequency sum and then divided by whole frequency. So this is just I have not written that formula in statistical manner, but here the formula means the same. What is that? See, the probability of occurrence the system in the un state, we are going to find that. Now in the apparent side you can see the system, as we know the probability of finding the system in quantum mechanics is your nothing but the wave function square. So cn un is the component of the wave function responsible for the state nth state. So cn square un square dx integration minus infinity to plus infinity will be in the numerator divided by the mod psi square. Psi is the total wave function. Psi is equal to Cn even sum. So psi is the total probability. It is determining the total probability of finding the particle or in the whole space. So if the two terms are divided to each other, then you will surely get the probability of finding the particle or the system in the nth state. Okay. So if I am not first in this case, you can assume that the psi is normalized. In that case, this is 1. Okay. If psi is normalized, then you will get the 1, that is the probability of finding the particle or the system in whole space for all the configurations will be 1. But I am not here assuming that the wave function is normalized, so that we can get most general result, and after that I will come into that point. Now let us do some mathematics. How? Mod psi square dx, look at this integration only. Okay, this is written over here, and here mod psi square can be written as psi star psi dx. And now in place of psi and psi star, you can replace the basis set expansion formula, that is your Cn psi n. It is not written here, it is written at the very beginning. Here in the equation number 1, you can see Cn psi n is your psi. So if you put psi in place of psi, you can put Cm un, and in place of psi star you can put Cn star un star, because two sums are multiplied to each other, so the indices are different for the convenience of the calculation. And this will generate two classes of terms, where in one class where n and m are equal, C in the first sum, and the second sum where the n and m are not equal to each other. This will construct this number of terms, and double sum will be there. So it is a very simple expansion of the two sums. You know, you have used this kind of calculation earlier, and now you know, if you assume that the basis wave functions, that is un, they are normalized, they are orthonormal set of functions, then this result should be 0, because un and um are not equal to each other in this sum. So the Kronecker delta will be appearing, and here if n and m are not equal to each other, then Kronecker delta will be 0, and so the whole result will be 0. In the same with the same formula of orthonormalization, this result will be 1. So the probability of finding the system in the nth state will be sum over Cn square. It is written after this. Here you can see, yes, this is written over here, and yes, okay, no, sorry, I was not completely right, because this mod psi square dx is your Cn square, mod sum over Cn square. See, here it is written. Okay, the second term cancels, 0, and the first term is 1, so sum over mod Cn square will be equal to the mod psi square dx integration. Okay, this is written here clearly. Now use this formula into the expression for Pn into the equation number 3. Here you know this is summation over Cn square, and what is about this term Cn square? You can take the Cn square out of the integration, and the left integration is and the integration is left with un square dx. So un square dx integration minus infinity to plus infinity, it is 1. So in the upper part, see, it is written over here, Cn square is taken out of the integration, this is the integration, and at the denominator we have already found this term, sum over mod Cn square, this is here, and this is 1 again. So the result, that is the probability of finding the system at the nth state, is your Cn square, that is the nth expansion coefficient square, divided by the summation of Cn square. And you can check this result whether the result is correct or not. How? If you take the summation over Pn, okay, where n runs from 1 to infinity, then sum will be on this term, because this is a constant term independent of n, but this is dependent on n, so the sum will be on the numerator, not the denominator. So numerator will be summation over n mod Cn square, and in the denominator already the term is there, so this will cancel and the result is 1. So what we will get here, this 1 is a very significant one, because summation over probability of finding the system in the nth state means you are going to calculate all the probability. That is, you are taking all possibilities of the system in every possible states, so the total probability will be 1, and mathematically also it is showing that the result is 1, and we have predicted that it should be 1. Okay, so the formula is very much correct, equation number 4, but equation number 4 can be simpler. How? If you assume that the psi x is the normalized wave function, I have not assumed that in the very beginning of this calculation, but now as a special case you can assume that psi x is normalized. So integration mod psi squared dx is 1 according to Max Born interpretation, and we have found that this integration is equal to sum over mod Cn square. So mod Cn square should be 1, sum of the mod Cn square should be 1. So in place of this term, you can put 1. So Pn is simply mod Cn square in this case. So equation number 4 and equation number 5 are both the expressions for the probability of finding the system in the nth state. In terms of the expansion coefficient, you need to find the expansion coefficient by some technique, and you will get the probability result. Okay, so but you should be cautious when you are using the equation number 4 or equation number 5. If the basis set expansion psi wave function is normalized, then you can use equation number 5. Otherwise you cannot use the equation number 5. This will produce some errorful result, and in this case you should use the equation number 4 for unnormalized wave function psi x. Okay, now we have what we have found, we have used the eigenvalue equation, we found the expansion coefficient Cn. How the expansion coefficient Cn can be determined, we have found it in the equation number 2. Here you can find the expansion coefficient. It is known to us because this integration can be done, and all the expansion coefficients can be find out. And now the second result is the probability. Also we have the probability expression, probability of finding the particle or the system in the nth state. We know all these things. Now we are heading towards our goal, that is the expectation value or the measured value in the quantum mechanics. These are the values through which an experimental result and the theoretical results can be tallied. So this is the main part of the quantum mechanics according to me. And let's start from the very beginning, that is the basis set expansion. And here you can the wave function psi is the eigenfunction of the operator alpha, and alpha is the operator form of a dynamical variable alpha. Here alpha op is here operator form, and un are the normalized complete set of normalized wave functions. Okay, so alpha un is equal to an un. So an is the eigenvalue corresponding to the eigenfunction un, or the set for each eigenfunction. You can form this kind of eigenvalue equation. I have already discussed about that. Now the expectation value is the average value. Okay, this is the average value of a dynamical variable from your classical point. Actually not classical, it is statistical. From the statistical point of view, we can calculate the average value of any quantity, say alpha, as this is the average value sign. It is not bracket sign, this is average value, expectation value sign, is equal to the value of that quantity into the probability of finding that value of that quantity, and the summation will be there. Okay, this is the basic statistical formula of any quantity, any average value of any quantity. Okay, so this is the basic formula, and here in quantum mechanics, you know the probability of the finding the system in the nth state is Cn square mod Cn square divided by sum over mod Cn square. From the equation number 4 it is written. So it is again generalized calculation. So psi x is not assumed as normalized at the very beginning of this discussion. So Pn is assuming the form of the equation number 4, not 5. 5 is a special case where psi is the normalized wave function. So there will not be this term occurring. Now Cn, you know Cn is equal to psi x un star dx. So Cn star will be what? Psi star un dx. Okay. So the first term is the numerator term is an Cn square. An Cn square. Let us start with the numerator. An Cn square. So in place of Cn square, mod Cn square, you can write this. Okay. So starts here. Sorry, starts from here. In case of mod Cn square, you can write Cn star into Cn. And in place of Cn star, you can use this integral. This integral formula is just put here. Now we are going further. How? The sum is now interchanged with the integration. Integration is taken out and sum is taken in. So the it looks like dx even star, because it is not a function of n. So it will be come out, and within the sum there will be Cn, an, un. Now an un is your alpha operator un because of the eigenvalue problem. In place of an un, I have written alpha into un. Sorry, alpha into un. Okay. Now alpha, because the operator is not dependent upon the n, so alpha can be taken out of the sum. So within the sum there will be Cn un. What is that? This is nothing but psi. So the numerator of this equation, okay, this term, we have found it. This is your dx psi star alpha operator psi. Now the denominator term. The denominator term is this, which is mod psi square dx. So in place of mod Cn square sum, you can write mod psi square dx. So the whole expression for the expectation value or the average value will be looking like this. The numerator is this psi star alpha psi dx. Here alpha is the operator. It is not a constant as you wish you can take out of this equation. No, it is an operator. It should be there in general, and in the denominator there will be psi star psi dx. Now the special case is that if psi is normalized to unity, then this term should be 1. This term, the denominator should be 1. Okay, so the whole result will be alpha expectation is your psi star alpha operator psi dx, integration from minus infinity to plus infinity. Now these results can be generalized into 3 dimension. If you are talking with 3 dimension, these integrations will be vanished and the whole space integration will be come into the place, and dx will be replaced by d tau, that is the volume element, and in the denominator also. So this is written here, you can see. Okay, if it is normalized, then again the denominator will be 1 and the result will be, oh, I have forgotten to write, and the result will be the just numerator term will be there. So the task is to so how we mathematically approach to the expectation value. Here it is written in this paragraph. Okay, see this, see from here, and some examples are there. Now I am describing from here. You can see taking the normalized wave function. First you have to know that of what dynamical variable you are going to find the expectation value. So if you know that dynamical variable, you will surely know from the quantum mechanics the operator form of that dynamical variable. So first operate that operator on the wave function. You will get a scalar number and multiply that scalar number with the psi star, which is another scalar part, and then integrate. This will give you the expectation value of that dynamical variable alpha. Okay, this is written here and with some examples. There are 2 examples. One, the expectation value of the x coordinate, that is x, and the linear momentum px, x component of the linear momentum px. From quantum mechanics, it is known that the operator form of x is nothing but x, so x is written here. So this integration should be done to find the expectation value of x, and for px the operator form is like this, h cut by I into del del x. So first operate del del x on psi, then it will form a scalar, then multiply that scalar into psi with psi star, and then integrate out in the limit minus infinity to plus infinity. This is the technique to measure, to evaluate the expectation value theoretically, and these theoretically expectation values are to be tallied with the experimental values, because experiment doesn't know how the values of the dynamical variables comes, whether it is coming from quantum mechanics, whether it is coming from Newton's law, or whether it is coming from Schrodinger equation, or whether it is coming from anywhere else. They do not know anything. They know how to measure the quantities precisely without any error or very minimum error. That's all. The theoretical part of those experimental determination is to find the expectation value in case of quantum mechanics. Okay. So now take some examples of measurement of expectation values. The first problem states you that a particle of mass m which moves freely inside an infinite potential well of length a has following initial wave function at t is equal to 0 is looks like this, where phi 1, phi 3, phi 5 are the orthonormal sets of eigenfunctions. So first of all, first of all you have to understand the infinite potential well means you know very well what is well. So from well we are we keep our water that is the water storage in our house. So you assume such well of infinite height, so any particle within the well cannot escape from that well. So these are called the infinite potential well. This is a very popular example of quantum mechanics, and this will be discussed in great detail in my forthcoming classes. But here the problem gives you the wave function with some expansion coefficients. See, this basically the wave function is expanded into a basis set, keeping three terms in the basis set, phi 1, phi 3, phi 5, with their expansion coefficients. You need not to evaluate from here, it is already given. So and the each state, it is the first excited state, this is the third excited state, and this fifth excited state, it is written here. Okay, so first excited, no, this is not first excited state, this is ground state, it is written. The energies corresponding to these states, if one wish to find the energy, because energy is a dynamical variable, one can find it. If one find it, find the energy value of the corresponding three states, that is 1, 3 and 5, that is ground state, third excited state and the fifth excited state, then the formula is given. Okay, where does this formula came? You don't need to think about it, just the formula is given here. En is equal to n square h car square pi square by 2m square. Okay, the A is the width of the well, m is the mass of the particle which is trapped within the well, h cut is the reduced Planck constant. Okay, and this is written again, I don't know why. If the measurements of the energies are carried out, okay, if the measurements, experimentally measurements are carried out, what are the values that will be found? That is, you are telling the experimentalist that you will get these values. How theoretical quantum mechanics can predict such values? With reference of what one experimentalist can set up their instruments. Okay, so this is the question, what are the values that are probable, and with what probabilities, what is those probabilities of having those values? And then the second question, calculate the average. First part first. Firstly, each of the states, find the energy values of each of the states. First, phi 1, that is the ground state energy E1, is just put n is equal to 1 in this expression, forget about this thing. Actually, I will show you later that energy values, energy eigenvalues or energy values of the quantum mechanical systems are the expectation value of Hamiltonian. Okay, I will show you later. Okay, so for the time being, just don't focus on this thing, it will come from the Schrodinger equation. Now just focus on these values. E1 is equal to n is equal to 1, put n is equal to 1, you will get this formula. For E3 you can get this, for E5 you can get this. Now the probability, how the probability is found? How? See, it is written in the bracket notation, and P1 is mod C1 square, because the wave function is normalized. How we know the wave function is normalized? See, C1 is what? It is not written elaborately. I will suggest you to do this sum with much more steps, so that you can involve yourself in this calculation. See, C1 is what? Root under of 3 by 5. C2 is root under of 3 by 10, and C2 not C3, and C5 is 1 by root 10. Is this set is complete? I have told you several times that you should take infinite number of wave functions to complete a set. Now take a look on this wave function. C1 square is 3 by 5, C3 square is 3 by 10, and C5 square is 1 by 10. Just sum them up. 3 by 5 plus 3 by 10 plus 1 by 10 will give you 1. And what is the probability of finding? See, from basis set expansion, if the wave functions are normalized, equation number 5, I think, yes, C1 square. So C1 mod C1 square is your 3 by 5, mod C2 square is 3 by 10, mod C3 square is 1 by 10, and if you add them up, you will get 1. So you need not take any other wave function into that picture. So although I was talking about the infinite number of wave functions, but sometimes the problem will be such that all possibilities will be nullified, all possibles will be can be neglected, because those 3 wave functions with those probabilities, root under of 3 by 5, root under of 3 by 10 and 1 by root under 10 is completing the set, because if you add those square values of the expansion coefficients, you will get 1. So there is no need to take other terms. It is a complete set. So because of that, we are going to use the equation number 5 to take each of probabilities, because the wave function is normalized. Okay. So the problem, I will suggest you that firstly check the wave function is normalized or not. For this you should check the bra psi, ket psi value, and you can see that it is 1. That means the wave function is normalized. If the psi is normalized, then you can use the formula P1 is equal to mod C1 square, P3 is equal to mod C3 square, or P5 is equal to mod C5 square directly. And what is the value of C1 square? You know, brush phi 1 and ket psi. It is written very I have discussed it very earlier in this class. Yes, equation number 2, you can see Cm, that is C1 is your U1 in the bra and psi in the ket. Psi is the total wave function. So this formula is used, equation number 2 has been used in this case to find the C1. Okay, then it will give you 3 by 5. Obviously this is the probability, is the again the probability, it's square are the probability, so 3 by 10 and 1 by 10 are the probability. So most probable state is your ground state, because it has maximum number of probability 3 by 5, larger than the latter 2. So the average energy will be the sum of P and N. This is the very basic formula of the statistical mechanics to find the expectation value or the average value of any quantity. Just multiply that quantity with the corresponding probability and take the sum. So P and N and E. So P and P1 is known to you, E1 is known to you, P3 and E3, then P5, E5 all are known to you. Just put the values of each of the terms. See, this is multiplied with this multiplied with this multiplied with this, and then sum, you will get this result. Okay, let us take another example of the basis sector expansion and evaluating the average energies. Okay, the question is, each state has the in the previous case, the energy values corresponding to each states are n square, pi square, h square by 2m square. But here the formula is given like n epsilon naught. Epsilon naught is a constant. Don't worry about this. This is not an electrostatic permittivity or something else. This is just a constant number multiplied by n, and this is basically the energy eigenvalue corresponding to the state n, and here we have taken 5 states. Okay, 5 states are here: psi 1, phi 1, phi 2, phi 3, with corresponding c's are there: c1, c2, c3, it is c4, it is c5. So first check, here you can see what I have told, that in the previous problem it is not checked that the total wave function is normalized or not, because if it is not normalized we should use the probability formula equation number 4. If it is normalized, then you should use the formula number 5 for the probability. So you have to be sanguine at your first step of the calculation whether the total wave function is normalized or not. It is checked in this case. See how it is checked. Bra psi ket psi is checked, and bra psi ket psi means the summation will be, the odd terms will be 0, because phi 1, phi 2, phi 3, phi 4, phi 5, these are obviously the orthonormal set, and it is written over here. So the cross terms will not appear in this sum. So phi 1, bra phi 1, ket phi 2, these terms are 0. So bra phi 1, ket phi 1 plus bra phi 2, ket phi 2, just like 5 terms will appear. So sum is there, n is equal to 1 to 5, and with the corresponding coefficients cn square, it is written as an here in place of cn. So simply these are the 1 because they are orthonormal, so an square mod sum over 1 to 5. So this square, this square, this square, this square, this square, just add them up, you will get the result of 15 by 9, not 1. So the wave function psi is not normalized. Okay, see, first note that psi is not normalized. It is proved by this equation. If it is psi is normalized, then this result should be 1. Okay, so we are going to use to find the probability of the particle in any state using the formula number 4. Okay, we can't use here the formula number 5. We have to use this result because the mod cn square sum is not 1 here, so you can't use this. You should use the general formula equation number 4. See, it is used here. Okay, so the each probabilities of each of the states are just c1 square by sum of cn square. So sum of cn square we have evaluated, that is 15 by 19. So in each case it is 15 by 19, 15 by 19 in the denominator, but in the above, that is in the numerator, the term will be different because c1 is your bra phi 1 ket psi. So bra phi 1 ket psi will give you at the first term, what is that, or c1, so you can directly put also this value of c1 square, that is 1 by 19. Okay, in the above you can put 1 by 19 and in the denominator 15 by 19. So 19 will cancel each other, 1 by 15. So it can be easily calculated from here, except writing this form you can write c1 square by mod of cn square. So in place of mod of cn square you can write 15 by 19, and in the above case, in case of c1 square you can surely write 1 by 19. In case of second case c2 square you can write 4 by 19. In case of so this will see 4 by 19 cancels and 4 by 15 will be the result. So this can be evaluated in more simpler way. You can use those, just you can write in this way, what is convenient to you can use. Okay, and the next task is to find the average value, average energy. Just Pn that is Pj Ej J1 to 5 you can write, because Ej, E1, E2, E3, E5 we know this. How? Here E1 is epsilon, E2 is 2 epsilon, it is given in the problem, n epsilon. So each values are known and each probability is unknown, So multiply them and you will get the result. 52 by 15 into epsilon naught will be the average result. If you repeatedly do the experiment on that system, which is in those states at can be in those states, and if you experiment on that system, so and repeatedly you experiment and took the readings, and then using the average value of the experimental setup, experimental data, you will surely get this result. The quantum mechanics is the authority which is telling you that if you go to the experimental lab, you will get this result if you prepare the system such and such. Okay, this is the power of this mechanics. And here another way to find the expectation value of energy, it will be shown later by me, I will discuss it later, that the energy is the dynamical variable, and its operator in time independent case, Schrodinger equation, it is the Hamiltonian of the system. You can use, there is an if the wave functions are not time dependent, as in this case the wave functions are not time independent, they are time independent wave functions. So in case of time independent wave function, you can use the Hamiltonian of the system as the operator. Okay, so operator operating on psi, this will give you En psi. Okay, and the result is the produced result is the same. I will come into that, you will understand after, that will be not easier to, here it is not easier for me to explain the equations why H operator operating on psi will give you the, or H operator operating on phi n give you En phi n. Because of that, En is come out of this term, and phi n is 1. So En into an square, what is an square? Here again an square is the probability, so my probability into the energy values will give you this terms. So this can be understood if you know the Schrodinger equation, time independent Schrodinger equation, eigenvalue form, then this will be easier, very easy calculations is very easily it can be written. But at this point of time I am not going into the detail, just remember the conventional way, or the way you know already, to find the average value or the expectation value. Okay, so in the today's class I have discussed about mainly on the measurement technique in the quantum mechanics, and how the measurements have been done. First, the eigenvalue equation for the nth state, then the expansion coefficient, how you will find it, I have described it, and then using the form or the formula of the expectation of the expansion coefficient Cns in the basis set expansion, you can find the probability of finding the system in any state, say n, that is Pn. The two formulas are there, one for the unnormalized wave function, and the other is normalized basis set expansion. And then the average value, how we will get the average value, and how the operators are involved to the expectation value or the average value formula of a dynamical variable. I have shown it, and using those all formulas we are able now to do some numericals. And at this point of time I would like to say thank you for listening.